Hi everyone, good morning, good afternoon, or good evening, depending on where you are located. And thank you for joining us for this AMETEK Solid-State Controls webinar. Today we're going to discuss understanding UPS systems. I've done this webinar before, but I've changed it up a little bit from the last time that we did it. So I'm just going to give everybody a chance to log in and join in. And if there's anybody on the call already, if you can let me know whether you can hear my voice loud and clear in the chat, that would be greatly appreciated. It just takes a few seconds for those comments to come in. Cool. It sounds like you can hear me. Excellent. As I said, as we wait for everybody to come in on this wonderful Wednesday morning here in Houston, Texas, I'll go over the introduction. So my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls, and I work out of the Stafford office, which is just south of Houston, Texas, southwest, if I'm going to be precise. I've been in the industrial UPS industry for over 20 years now. The first 10 years I was in the North Sea oil and gas fields, going from platform to platform, doing installation, commissioning, and maintenance and repairs on UPS systems. And I've worked with all the major UPS charger manufacturers in the last 20 years. And I joined AMETEK Solid-State Controls around about 6 years ago. There will be a lag of around about 30 seconds between you hearing my voice and me seeing any comments in the chat. We use a platform called Webinar Jam. It seems to be a very good platform, but what they need to do is they need to transmit this webinar on iOS, Android, and on Windows-based systems. So they do have to do some file conversions in that time and then get it out to everybody. So there is a lag from when I speak to when you will hear my voice, and it's around about 15 to 30 seconds. So that means that for me to be able to see the chats, there's going to be a delay. So we usually wait until the end of the webinar to go over any of the questions that have been asked. The ideal place to put any questions is in the Q&A section, but if you also put it in the chat, I'll be able to see them. Webinar Jam, the webinar platform, has a panic button. So if I see that people can't hear me, or for some reason somebody lets me know that there's an issue, what I can do is I can press the panic button, and that kicks everybody out of this room. It starts a new room and invites everybody back in again, and we start from where we left off. A very popular question is, will the webinar be recorded? And the answer to that question is yes. Webinar Jam actually records the webinar as we go, and then as you have registered for the webinar, you will be sent a link to replay the webinar whenever you want. The only problem with the Webinar Jam replay is that you can't fast forward, rewind, and move through the webinar at your own pace. You press play and it's just like the webinar has happened again. But what our fantastic marketing team do is they download that Webinar Jam video, convert it to an MP4, and then upload it back up to the AMETEK Solid-State Controls YouTube channel, where all of our webinars live. So they will post the link for that in the chat bar. So it takes them about 24 hours to convert the video and then post it on YouTube. So it should be ready around about tomorrow at the latest. And the last thing is the webinar should last around 45 minutes to 1 hour. I really am trying to reduce the time of the webinars so people I know that everybody is busy, and for me to take an hour and 30 minutes out of your day, which I tend to do sometimes on the webinars, is not great. So I'm trying to keep it down to about 45 minutes, hopefully today, and then some time for Q&A. Somebody has asked us, will there be certificates sent out for continuing education requirements? I don't think we have that set up yet, but I'll let our marketing team answer that for you in the chat. Okay. So let us move on. So the agenda today is we're going to discuss the power flow and general operation of UPS systems, discuss the major blocks inside the UPS system, and then we're going to have a Q&A session at the end. So it's not a very slide heavy presentation today, but hopefully we're going to go over some good information and prompt some good questions. So in a normal industrial UPS system, the components that are inside there, in general terms, are, as you can see on the screen here. So first of all, you will have a normal AC input, which is also called the primary supply or the main supply. That is the power that gets fed to the rectifier battery charger. The next thing we have is the battery charger rectifier, and that converts that normal AC into DC and charges the batteries. And we'll get on to how they do this in an overview way in just a moment. Then inside the UPS, well, usually external to the UPS, but part of the UPS, there will be batteries. That's the heart of the UPS. If you don't have batteries, then you don't have a backup power supply. So the batteries provide backup power during a loss of grid power. Then that DC needs to be converted back to AC because it's AC loads. The critical loads that we supply are AC loads. So the inverter converts that DC back to AC. And then we also have a bypass source or an auxiliary power source, which can also be called a reserve supply. They are all interchangeable terms, but they mean the exact same thing. It's a backup AC power supply that is not backed up by the battery. That's important to remember. It's just fed usually directly from a grid. Sometimes it's fed from a power conditioner, but it does not have any battery backup unless you have a cascaded redundant system, but we won't go into that today. The next block is the static transfer switch, and that's an automatic switch inside the UPS that connects either the load to inverter or the loads to bypass. It is a switch, but it has no moving parts, so there are no contacts inside the switch. We use SCRs, which are semiconductor devices. They're silicon-controlled rectifiers, and all we need to do is send an electronic signal to them, and they turn on instantaneously, and that way we can transfer between inverter and bypass seamlessly without a break in power. And then, not to be confused, the static switch should never be confused with the manual bypass switch or the remote manual bypass switch. The static switch is electronic and has no moving parts, but the manual bypass switch, remote manual bypass switch, is a make before breaks mechanical switch that removes power usually from the UPS cabinet to allow safe maintenance. And this can be a rotary switch or a breaker arrangement, depending on the manufacturer of UPS you have. But for AMETEK solid-state controls, it is most of the time a rotary switch. Okay. So here is the one-line diagram for double conversion industrial UPS. And I know, once again, I hate big, long words because it tends to make things a little bit more complicated than they should be. But when we say double conversion, what we're saying is that we convert the power twice. So in other words, we change AC to DC in the battery charger rectifier, and then we change that DC back to AC in the inverter. Okay? So that's why it's called double conversion. We change the power twice. Okay. And for an industrial UPS, one of the things that is the big difference between a commercial UPS and an industrial UPS is you should see isolation transformers on the input and on the output. Because what we have in here is we have a DC bus. And if you have any kind of failure in the battery charger rectifier in here that allows DC to get back onto the AC, that could cause havoc on all the loads fed from your MCC and would cause a huge amount of issues inside the plant. But with having this transformer here, there is no electrical connection between the primary and the secondary. So that prevents any DC getting back onto the MCC that feeds the AC input. And this transformer here prevents any DC, if there was a failure in the inverter, getting onto your AC load circuits, because an isolation transformer will not pass DC. It's impossible. So that's one of the main differences between a commercial and an industrial UPS. What we're going to do is we're going to go over each of the blocks inside of this UPS one at a time as we go through the slides. Okay, but first of all, what we're going to do is go over the power flow of a normal UPS in its different modes of operation. And on the screen here, you'll see that we have red, and down the bottom right hand corner you can see the key. If you see red, there is power flowing, and if you see green, it is energized and ready, but there is no power flowing. Okay, so in normal operation, you can see that power comes from the AC input here, comes into our battery charger rectifier, and then the battery charger rectifier will regulate the output voltage, the DC voltage, at what is required to charge the batteries. In truth, the inverter doesn't care what that voltage is. Now, yes, it does have to be within certain specifications, and for us, it is usually 105 to 140 volts DC for a 60 cell system. But in truth, AMETEK SCI could make an inverter that operated off 50 volts if they wanted to. But for our UPSs, this is the realms that we usually stay between. The batteries are charged at what the batteries require. So most lead acid batteries say that it should be 2.25 volts per cell. And if you multiply that by 60, the float voltage will be 135 volts DC. So that is why the DC bus is 135 volts. Okay, it's the only reason why, because the 60 cell lead acid battery is the most common in industrial applications. Now, the connection between the battery and the rectifier and the inverter, they're all in parallel. So the DC bus also feeds, not only does it feed current to the battery, but it also feeds current into the inverter. And the inverter changes that DC back to AC. Then it goes through this isolation transformer, which has some filtering in it, and then you get a perfectly beautiful sine wave on the output there. And then here's the static switch that I mentioned earlier. That static switch will be on, so power will flow out through here to our AC output, which is your critical loads. Okay, so that is normal operation. And then we also have our bypass source AC input, or our reserve supply. We can see that this is energized and it's ready to go at this static switch here, but this static switch is off. It doesn't need to be on just now. So it is there waiting to go. The inverter has synchronized itself to the bypass supply, and we'll get to that later on. And if necessary, we can transfer to bypass if there was a reason to do so. But at this moment in time in normal operation, the bypass just sits there, is ready to go, but it is not supplying any power. Okay. Now, this diagram here shows you what happens if we have an AC input power fail. So what you will find is in most well-designed systems, the AC input will come from one MCC and the bypass source input will come from another MCC to give you some redundancy. So in this example, what we're saying is, let's say that the MCC that feeds this AC input here has been taken down for maintenance or has had a failure and the MCC has had to be completely shut down. Let's say the transformer feeding the MCC has failed or something like that. Okay. So the AC input power to our rectifier battery charger has been lost. So what happens is, now a lot of people say that then it switches to battery. There is no switching here that happens. It's just as if, I'm sure everybody has a laptop these days. If you pull the power out of your laptop, it just continues running as normal because the DC bus in that laptop is in parallel with the battery. And that's exactly what happens inside our UPS systems. As soon as the charger loses power, the batteries just continue taking the load without any issues whatsoever. There's no switching. They just take over supplying current to the inverter. And you'll notice that the inverter stays on because the inverter is the most reliable form of power we have, because we know that this inverter, if it is a single phase system, will give us 120 volts AC. It's a beautiful sine wave that is regulated at 60 hertz and everything will be fine. Okay. And then the power flow is just the same as it was in the previous slide from the inverter onwards. Now, some people say, well, wait a minute. You know, it's only this MCC that has gone out. We still have our bypass source available. Why don't we transfer to bypass and save the batteries? That's a very good question. And the reason behind it is, as a company, as a UPS manufacturer, we have no idea why this AC input has gone out. It may well be there has been a catastrophic event in that MCC and many other loads within the plant have been switched off, or many other pumps are starting or being turned off. So it could well be that the power in the plant is very, very unstable and the frequency is going all over the place and the voltage is going all over the place. So the bypass voltage could be very unstable. So we don't want to transfer to bypass in that circumstance, because it doesn't matter how unstable the bypass is. Our inverter doesn't care about that. It's putting out a beautiful sine wave at 60 hertz, unaffected by what's going on in your plant. And we can guarantee that the power going out to your load is regulated and exactly what your load circuits need. Okay. So that is why we don't transfer to bypass. We stay on inverter. The UPS does everything it can to try and stay on inverter as much as it possibly can. Okay. So let's say the AC returns before the battery completely discharges or before it completely depletes. All that happens is the sensing inside the battery charger rectifier sees, okay, I now have my 480 volt AC back in again. So there is no switching involved. There is no interaction with any plant staff at this point here. The battery charger just says, okay, I've got my power back, and it switches itself back on again, and it will start to recharge the batteries and go back to feeding the power needed for the inverter. Once again, no switching involved whatsoever. You don't have to turn a switch on. You don't have to set something up to do this. This is done automatically within our system. As soon as it sees that the AC is good again, it goes back to normal operation. But let's say the AC was out for a prolonged period of time. So let's say the AC has been out for about 5 hours now, and depending on the size of your battery may be getting to the stage where it is depleted. And for a lead acid battery, all the battery manufacturers say that you should not discharge a lead acid battery below 1.6 volts per cell. You could do irreversible damage to a lead acid battery if you go past 1.6 volts per cell. And in truth, the industry standard when people size a UPS is that the low voltage cutoff is actually 1.75 volts per cell to give you a little bit of a buffer. So what AMETEK solid state controls do as a manufacturer, and what other manufacturers do, is that they say, okay, we're going to set up a circuit within the system, and it's actually within our inverter control board here, that's monitoring the DC into the inverter. And if you times 60 cells times 1.75, you get a voltage of 105 volts. And what the inverter control board does, it says, okay, if the DC bus goes below 105 volts, I am going to trip this DC input breaker and disconnect the batteries, because that is the only way we can protect the batteries from being over discharged. Okay, but our inverter is clever enough, before it trips this breaker here, it says, okay, well, what we need to do before we trip that breaker, we need to transfer over to bypass. So we turn this static switch on, we turn this static switch off, and there is an overlap. You know, when we turn the bypass static switch on, it is on the same time as the inverter static switch is on for half a cycle. And then the inverter static switch turns off. So it is a seamless transfer to bypass. And then we trip the battery input breaker. That way we can guarantee that your AC load circuits continue to be powered, and they will not notice that there has been any change inside the UPS whatsoever. Your load circuits will be maintained throughout this process. And then the final mode of operation, let's say there was something wrong with inside the UPS and you switched off the AC input, you've switched off the battery, and what you want to do is you want to get to the system into what's called manual bypass. Therefore, we're going to the bypass source, but not through the static switch anymore, because maybe we want to do some repairs on that static switch. We are going around that static switch through the bypass switch. And this bypass switch is a make before break switch. And what it does is it just goes from this position here over to this position here. It makes the connection and then it breaks that connection. Okay, so once again, your load circuits will not see any power interruption whatsoever in this situation. So now we're going to discuss or have a very small overview of the battery charger rectifier. I'm going to show you the circuit diagram and go through a couple of things. Just going to take a drink of water first. So as you can see on the screen there, the orange block is the battery charger rectifier. And this is the schematic diagram. Now, I know it does look a little bit busy, but I'm going to go through what's going on here. So you can see here, this is where our 480 volts AC input comes in. And please remember, we do not run a neutral to the AC input to our UPS for the battery charger rectifier. There is nowhere to land a neutral inside. It's just 3-wire and ground that gets run to our UPS systems. And then we have our delta primary. This is the isolation transformer that I talked about earlier on in the presentation. And you can see there is absolutely no electrical connection between the primary and the secondary. Okay, the secondary is a separately derived source. There is no electrical connection whatsoever. So there is no way anything can feed back this way, DC wise, through that transformer. It's absolutely impossible. Okay. This transformer does step the voltage here down to about 120 volts phase to phase for a 60 cell system. So you will have AC still going in at this point here. But now inside our battery charger rectifier, we have 6 SCRs. I can't point at the ones above here because my screen cuts off. It's just the way that Webinar Jam screen is. But there are 6 SCRs here, and that's our switching devices that turn the AC on this side into DC on this side. It really is as simple as that. In the grand scheme of things, it's as simple as that. Now, there is some complex circuitry going on with the charger rectifier interface board and our charger gate drive board, but it is as simple as we have AC on this side and we have DC on this side. Okay, and you can see that we have 2 branches. One, this one up the top here, this goes to the inverter, and then this one here goes to our battery. Okay, they are connected in parallel, they're the same points. It's just one, we want to have this disconnect here going to the battery, and the inverter supply just goes directly to the inverter through those fuses. So that is the charger inside our UPS systems. If you want more details on how our chargers work, we do have another webinar inside our YouTube library at the AMETEK Solidstate Controls YouTube channel. If you want to know more about how our chargers work, go there, check it out. And I might do another one this year sometime. Okay. The next block is the inverter. Okay, this converts the DC that the charger just made back into AC. So you can see here on the left-hand side, we've got our positive over here, and we have our negative over here. So this is our DC. And then instead of having SCRs, we now have 4, because this is a small system, we have 4 IGBTs, which are insulated gate bipolar transistors. And this is what changes the DC back into AC. So we have this inverter static switch control board. It sends the signals to these IGBTs and tells them when to switch on and off. But in the grand scheme of things, it's quite simple to remember. We have DC on this side, and then it goes through this transformer, and we have beautiful synthesized AC sine wave that is filtered and has very low THD, total harmonic distortion. It's just a very, very clean sine wave that your load circuits can rely on. So in the block, that's all you've just got to remember in this drawing here. We've got DC on this side, AC on this side. And once again, if you want more information on how these inverter bridges work, how the IGBTs work, you can check out the inverter video in the YouTube library. And there's also a semiconductor video in our YouTube library that goes over how each of these semiconductors, the SCRs or the IGBTs or diodes work. So I really recommend that you go and check those out. Okay. And next we have our static switch. Now remember, static switch, static does not mean static electricity. Static means no moving parts. Static as in still. There are no moving parts. Okay. So you can see on this previous drawing, we have one static switch here and one static switch here. This is the inverter static switch, and this is the bypass static switch. Okay. In the schematic drawing, it's drawn a little bit differently, but it's still the same. On this one here, this is the inverter static switch. I just know that because I know wire 17 and 15 come from our inverter. But I do know that it says down here, our bypass input is down here. So if we follow this up, it goes up through this bypass input breaker, up through here, in here. So I know for sure that this is our bypass static switch. And then you can see that the output of both static switches is connected together. And that is our common bus. That is our critical bus, basically. We can swap between inverter supply or bypass supply, and we will maintain the circuits out to our critical loads that are connected to the AC output here. Okay. Now, to transfer the static switch, there are many circumstances where it is done automatically. We are always sensing the input to the inverter static switch, and if the UPS feels that it is out with tolerance, has gone completely, if the inverter has failed, there are many situations where the system will automatically say, okay, the inverter static switch input power is not good, so it will immediately switch over to our bypass supply automatically, seamlessly, without a break in the sine wave going out here. Because you have to remember that the inverter, so this one here, the inverter synchronizes itself with the bypass supply here. It's always trying to stay with the bypass supply as long as the bypass supply is within tolerance. So that means frequency, phase, displacement, and voltage. If the bypass is within tolerance, the inverter will do everything it can to stay in sync. Because remember, if we are on inverter and we want to transfer to bypass, what happens is when we press the bypass to low button, or the system does it automatically, this static switch comes on first. So these two static switches will be on at the same time. So they have to be identical waveforms or they would be circulating current. So they are identical because they're in sync. And then as soon as this one turns on, this one will turn off. And therefore it is a seamless transfer. Okay. Next up, we're going to discuss the manual bypass switch, or the manual bypass switch and the remote manual bypass switch. And I'll discuss the two differences in just a moment. But please remember one thing. A manual bypass switch and a static switch are two completely different components. They have no relationship to each other. In other words, what I mean by that is the manual bypass switch has no interaction with the static switch, and the static switch has no automatic interaction with the manual bypass switch. Okay, they are two separate things. They should be considered two separate things, and I'll explain why in just a moment. I'm going to take another drink. Oops, I went backwards. That's not. Did I go backwards? No, I never. One moment. So this is the same drawing that we had for the static switch. So you can see once again, here's our inverter static switch, and here's our bypass static switch. Okay. But you can see here we have switch 1. Okay, and we have two contacts for a manual bypass switch. And when I say a manual bypass switch, that refers to a bypass switch that is actually internal to the UPS. It's on the front of the UPS panel. So it's part of the UPS itself. We are getting away from that design. That used to be our old design where we had a bypass switch on the front of the UPS. But basically, we are encouraging everybody to get away from that design and move to a remote manual bypass switch, which I'll discuss in just a moment. But when I say a manual bypass switch, not a remote manual bypass switch, then I mean it's inside the UPS. Okay? So you can see here in normal operation, this switch 1 is closed. Okay? You can see right at the top there, it just shows you what position the switch is in. So in normal position, it's saying that this switch here is in position 1, so it's closed, okay? And this switch here is open. So that means in normal operation, power would be flowing through the inverter static switch down here and then out through this contact here to the loads. Okay, our bypass supply is coming in here. It is ready to go at that static switch, but it's also coming along here and it goes to that side of the contact on the switch, but it can't go any further because that switch is open. So in normal operation, that is how the arrangement of the manual bypass switch. Now, if we need to do some maintenance inside the UPS or a repair or something like that, in many cases, we want to shut down the UPS and we want to get into what we call manual bypass or maintenance bypass. So what we do in this circumstance is we will at first, and every procedure that is on the front of our UPS systems will tell you to do this first, and that is transfer the system to bypass using the static switch. So remember, this is the static switch. So you would press the bypass to load button on the front of the UPS, and that would switch off the inverter UPS, the inverter static switch. But before that one went off, the bypass one would be turned on. So power would be flowing now up here through this static switch out to our load circuits. You say, well, why is that important? It's actually very important because now when you follow this one down here, we have bypass on this side of the switch, and you can see we have bypass on that side of the contact inside the manual bypass switch. And bypass are the exact same. They have to be, because they're the same supply. They are the exact same frequency, the exact same voltage, and the exact same phase relationship. It's impossible for them to not be the same unless it's been the system's been connected incorrectly from the start. It's basically impossible. So we know now if we close this contact here that we are paralleling bypass and bypass together, and it will be a seamless transfer because this is a make before break switch. So what happens is this contact closes first, and then this contact here will open, and therefore instead of power flowing up here, that's not the way it's going to flow anymore. Power is now going to flow through here and out here. Okay, that means we can go inside the UPS and switch all the other circuits off, and we can make the SCRs volt free, we can make the inverter volt free, and we can make the charger volt free, and the power will still go out through the load circuits from your bypass supply. So that's on a manual bypass switch. But what you have to remember is that means, remember, this switch is on the UPS itself. So that means we are going to have power going to the contacts of these switches. So that means the UPS cubicle is not going to be completely volt free. And in those circumstances, if any of our field service guys come out and have a look at your system, we'll take an electric blanket, insulated blanket with us, and we'll cover those terminals to make sure there is no exposure to live terminals or arc flash. So you can see that it's not the best situation because we still have power in the UPS. So what we recommend you do, as I mentioned earlier, is get an RMBS. Okay, so this drawing here, it's the same UPS that we had before. Power flows out through this terminal here, out through our our remote manual bypass switch, and you can see that that contact there is closed, so it will go out through here and out to our load circuits. Okay, and then on this system, our bypass goes through a transformer. It comes down here, goes through the RMBS, and this is closed, and it goes and supplies the bypass to the static switch. Okay, and this contact here is open, and we'll explain that in just a moment. But you can see now that the bypass switch is completely separate from the UPS. Here's our UPS enclosure here. This could be in a different room if necessary. In most cases, it's right next to the UPS, but it is not physically connected to the UPS usually. It is remote, and therefore, if we follow the procedures, we can actually make this whole UPS volt-free and work in it safely. And here's a simplified drawing of a remote manual bypass switch connected to a UPS. So remember, this section here is the RMBS, and this section here is the UPS. Okay, so you can see that first of all, our bypass comes from your MCC. It comes in and goes through the contact and comes here, goes into the bypass static switch. And remember, this is usually off, so it just stops there. Okay, and then the inverter is usually supplying power through the inverter static switch. Power will flow through here. You can see that this contact here is closed, so it will go through here and out to our load circuits. And you can see that this contact here is closed just now. Okay. And then here is the key to the positions that we have on the switch. Position 1 is normal operation. Position 2 is bypass to load. And position 3 is what we call isolated bypass. Now, once again, there is a webinar in our video library on our YouTube channel that describes everything that you need to know about an RMBS. But in general, what I want to show you is how to get from normal operation to bypass. Now, once again, the UPS is going to have its procedure, and it's going to say you're going to be going through here just now. So we are on inverter static switch, and the bypass static switch is going to be off. Okay. The first thing that the procedure is going to do is tell you to press the bypass to load push button. That turns this static switch on and turns this static switch off. So what will happen is bypass will flow through here, down, still inside the UPS. So we still have power and voltage inside the UPS. It will come out here, come through here, and go out to your load circuits. Okay? So that is in position 2. Okay, you can, if you, once again, if you look at the switches, it says down here, it tells you what position the switch will be closed. So this one here says position 2 and 3, this will be closed. And up here, it says position 1 and 2, it will be closed. So once again, our power is flowing through here when we press bypass to load push button. And it's important because, once again, remember, that means you are going to have bypass here on this side of the contact, and on this side of the contact, you're going to have bypass as well. So when we move from position 1 to position 2, which is a make before break, this switch here closes, parallels bypass and bypass together, which isn't a problem because they have the same voltage and frequency. And then instantaneously, it will open this contact. Okay? So in that circumstance, when we move to bypass to load, what happens is power flows through here, down through this contact, excuse my terrible drawing, and out through here. Now remember, this is now open, so no power flows out that way anymore. Okay? This terminal does not have power because of that switch. And the last, the great thing about an RMBS is the isolated bypass position. Okay, so remember, Power is flowing down here through here at this moment in time because we're in bypass to load. If we move to position 3, you can see here, position 3, this remains closed. But what happens is this contact up here, and excuse my drawing, this one here opens. Okay, so power is now actually flowing here, down here, out there. And now there is no power here, and there is no power here. So what we can actually do in this circumstance is we can go in, we can switch off the inverter, we can disconnect the batteries, we can switch off the AC input, and now we can make this whole UPS system volt-free so we can do in-depth maintenance, troubleshooting, repairs, and in truth, we can replace that UPS if absolutely necessary. Because here's a better drawing for you to see what's happening. If we are in the bypass isolated position, so this is open, power is flowing down here and out there. Terminals 110 and 115 have no power. Terminals 199 and 15 have no power. We're going to go in and we're going to disconnect the battery, so there's no power. We are going to disconnect the AC input. There is no power. Okay, so therefore what we can do is we could actually go into the UPS, we could lift that cable, we could lift that cable, we could lift the battery cables, we could lift the AC input cables and completely remove this UPS, install a new one while the load circuits are still powered up. So it gives you so much more flexibility in your plant when you have a remote manual bypass switch. Okay, so hopefully that explains a little bit more. And like I said, go to our YouTube channel. There is much more information on there about remote manual bypass switches. Wow, 45 minutes exactly. It's not like me to stay on track. So that's a general overview of UPS operation. What I'm going to do now is go through the questions that we've had, if we've had any. And if you have any questions that have come up during this presentation, please let me know. Okay, so let's start here. Why are isolation transformers not used in commercial UPSs? It's a very good question, Nathaniel, and it's 2 reasons. Cost. Transformers use a lot of copper, so the commercial UPS manufacturers can sell their UPSs for a reduced price because they don't have 2 big lumps of copper inside their UPSs. And the other reason is footprint. The commercial UPS manufacturers are trying to make their UPSs as small as they possibly can to fit in really tight spaces, because they're generally designed, the commercial UPSs are more for data centers and things like that, where space is a premium. I know space is a premium in most places, but in data centers even more so. So they're trying to save cost, and they are trying to reduce the size of their UPS. And what they'll do, a lot of the commercial UPS manufacturers, they'll turn around and say, well, you can buy our UPS, put an isolation transformer external on the input and an external one on the output, and then it becomes an industrial UPS. Well, you've just had to pay extra for the transformers, and the size of the installation has now gone up. So in my opinion, they're just trying to pull the wool over industrial customers by saying that you should do that. I'm not biased, I promise. I'm just saying that's what they do. Hopefully that explains the question, Nathaniel. What problems would be caused in an industrial UPS if there were not isolation transformers? Once again, if there is a failure, a short circuit within the rectifier section or a short circuit within the inverter section, then that DC bus could, in theory, if there isn't protection put in place, could put that DC back onto your AC supply. And when that happens, it could cause havoc at your MCC or at your AC load panel. So that's one of the major issues if you don't have transformers. The second one is a one that many people don't realize and understand, especially on the older commercial UPSs. If you don't have an isolation transformer on the input going to your charger, then you are not separating the AC and its reference to ground with respect to your battery. And what you will find is, because an SCR in a battery charger is just a switch, and if you think about it for a moment, if you are just switching that AC using an SCR, then if you don't have a transformer, there will be an AC content going to your battery. Now, your battery won't see it because it's with respect to neutral or respect to ground. Now, I don't want to get too complicated with this. I hope I explain this correctly. But depending on how phased on those SCRs on, let's say they are phased half on, and your input is 480 volts, you could see 240 volts AC with respect to ground on your battery. So if a technician went out to do maintenance on the battery and wasn't careful, and he touched a battery terminal, he could be shocked. He or she, sorry, could be shocked with 240 volts AC with respect to ground. So basically, if he touched a battery terminal and his arm also touched the rack and there was an exposed part of the rack, then he could definitely be shocked. I've seen it. I've actually been caught out by this when I was very young in my beginning career. I was wondering why I got a shock off a battery when I shouldn't have. And it was because there wasn't an isolation transformer on the input to the rectifier. So a lot of commercial UPS manufacturers have got away from that by inserting a DC to DC converter between the charger and the battery, and that gives isolation. But with the problem with that is a DC to DC converter is an electronic component, which is a single point of failure. So, and it's right between the battery and the inverter. So it could actually be, if that fails, you have no battery. And that's not possible with our industrial UPS systems. So Jamshid has asked, what is the THD level at the input and output of the UPS? Is there any DC chokes? That depends on the UPS manufacturer. You'll find that in the spec sheet for the UPS. I think for our DPPs, it's less than 3%. I don't think I've got a data sheet. Let me see. No, I don't have a data sheet with me just now. Oh, actually, yes, I do. Right, DSC, let me see if it has THD listed. Okay, less than 5% for our ferroresonant designs, and I think it's less than 3% for our DPP designs. But all UPS manufacturers are different. And yes, there are DC chokes inside. Most manufacturers will have a DC choke to reduce the THD. And some manufacturers are going to IGBT active controlled rectifiers, which reduces the THD level even more on the input to the UPS. In truth, in industrial plant systems, it's not really too much of a consideration, but in data centers, they really want to get the power factor and the THD to as low as possible so they can save money because they're using so much energy. Another question from Jamshid. Can the output frequency of the inverter be adjusted to something different? It depends on the manufacturer. For AMETEK solid-state controls, the free running frequency of the inverter can be adjusted slightly, but not by a huge amount. If you buy a 60 hertz system, it will come at 60 hertz. If you buy a 50 hertz system, it will come at 50 hertz. There is some adjustment, but we don't ever recommend anybody changes that because it's called the free running frequency. If there is no bypass supply to synchronize to, it will run at exactly 50 hertz or exactly 60 hertz using its own internal clock. Hey Cameron, how you doing? Question from Cameron. Why use IGBTs versus SCRs in the inverter? So SCRs are very, very robust, reliable devices. And that is how the inverters, how most inverters switch the DC to AC originally was using SCRs because IGBTs hadn't come out. So it was only in the, I think it was in the 80s that IGBTs started to get to a point where they could supply high enough power to be used in industrial UPS applications. So switching SCRs is very, very difficult because you can switch an SCR on, but you can't switch an SCR off. And if you want more information on that, go to my semiconductor webinar that's on the YouTube channel, and you'll find out more. And so therefore, if you connect an SCR in series from a battery with a lamp, and you send a signal to the SCR to turn on, the lamp will turn on. But if you remove the signal from the SCR, as long as the DC from the battery is still there, the SCR still stays on. You know, you've removed the signal, but it does not turn the SCR off. The SCR will only go off when it goes past a zero crossing point, or there is no current flowing through the SCR. So therefore, because in an inverter you're changing DC into AC, we have to force the SCRs to turn off. And we do that by something that's called reverse commutation. And basically what we do is we use a capacitor to force current in the opposite direction to turn the SCRs off. And it's, I wouldn't say it's complex, but it's we can't do it with PWM. We can only do it with a very basic square wave with SCRs. So the output of an SCR inverter bridge is not as smooth and has more THD, or total harmonic content, than an IGBT PWM bridge. Okay. So when IGBTs got powerful enough to be used in high power UPS applications, you can switch an IGBT on and off all day long at 8,000 times a second, 15,000 times a second, however you want to do it, depending on what type of IGBT you use. So it allowed the UPS manufacturers to go from a very rudimentary square wave inverter to a pulse width modulated inverter, which creates a much smoother, highly regulated output. So a long answer to a very short question, Cameron. That is why we use IGBTs in the inverter bridge now, because they're more reliable, easier to switch, and give us a better waveform on the output. And for most square wave inverters, you've got to put that square wave through a ferroresonant transformer as well, which adds I suppose inefficiencies, because a ferroresonant transformer runs a little hot because we have to saturate it to get it to be a constant voltage transformer. And the last question I can see so far is from Cameron again. Why not both use an internal MBS and an RMBS together? That's actually a very common question. Let me go back to this one, this screen here. Okay, so we do, in this picture here, we do have an RMBS and we have an MBS. And so you can use them together. But what happens is the operating procedure on the front of the UPS confuses the operators at the plant, because when it says move the manual bypass switch to the bypass position, does it mean this one or does it mean this one? And it gets confusing. So what we always do is, whenever we install an RMBS on a system that already has an MBS, acronyms, PWM, IGBTs, it's acronyms all day today. But whenever you have both switches, what we recommend you do is you actually go to the MBS on the UPS, unscrew the handle, take the handle off, and leave this in its normal position and forget that it was even there. Okay, so it will stay in this position forever, and then we can use the RMBS to do all the switching. So the answer to your question, Cameron, is to avoid confusion, because confusion can cause load to be dropped, and that is something that we don't want to do. So hopefully that answered your question. Okay, we've got a few more questions coming in. So how can we emergency shut down a UPS? Is it removing the optical fiber cable from the static switch when our display board is not working and the system to transfer to the alternate line? So good question, Abdul. In our DPP systems and in our DSE systems, so in all of our modern UPS systems, we have what's called a crash pad on our inverter static switch control board. So there are two black push buttons on the inverter static switch control board. One says inverter to load and one says bypass to load. So if you are in a situation when the display board is not working, if your screen is not working and you don't know what's going on, then what you can do is you can open the door of the system, find PCB3, which is the inverter static switch control board, and press the black bypass to load push button, and then that will get you into static bypass, and then you follow the procedure to get the system into manual bypass. And then you can reset the screen, do whatever you want, and then follow the procedure to start it back up again. So is the AC output actually PWM? Another question from Nathaniel. No. Good question, Nathaniel. The output of a system is not PWM. If we go back to that drawing. I love it when people ask great questions. So here's the drawing here. So it is PWM on this primary side of TF2, okay? Now, TF2 has built-in inductance. We actually add inductance specifically for filtering, and it has C2 here. So the inductance and the capacitance on the secondary of the transformer here convert this PWM into a beautiful sinusoidal sine wave. So the answer to your question, Nathaniel, is no. The output is a pure sine wave on a PWM system. Okay, Skip. You have a customer that always has both an internal and a remote MBS. Do they get supplied the correct instructions for this? What you would have to do, Skip, is if they have added a remote manual bypass switch to their system and they still have an MBS, you will have to get with the factory and have a new placard made for that. So going forward, if you ever are in a situation where you are recommending a customer changes over and adds a remote manual bypass switch, then somewhere in the communication with the factory when you order it, make sure that they add a new placard for the UPS to add the instructions for the remote manual bypass switch, because you are correct, it is confusing, and it's very easy for us to make a placard. You do have to place an order for it, so the people who make the placards know that they have to make one, and the engineering team should be able to write that new procedure for you without any issues. Okay. That is all the questions I can see so far. So what I will do is remind everybody that this webinar was recorded. It will be converted into an MP4 and it will be uploaded to our YouTube channel. London is going to post that link in the chat bar once again if you want to go and see this video or any other video, webinar videos that we've made over the last 1.5 years, 2 years. The video won't be available until tomorrow because there is a conversion process that has to be done. But if you want to see this tomorrow, you can go to our YouTube channel. If you have any questions or concerns that you think about after the webinar is finished, you can reach out and contact us. London will also post that, the contact details in the chat bar for you. It's, I can't remember if it's service@SCI. Let me see, she's posting it somewhere. I think it's service@SCI, at AMETEK, SCI, at service@ametek.com. Or you can go to, so it's sci.marketing@ametek.com. Sorry, that will get you to the right person. You can call us at 1-800-635-7300 and you will be directed to a human being. Believe that, a human being. And they will answer your calls between 8 and 5. And it will go to our call center after hours, and they will get one of our technical managers to call you back if it is an emergency. And you can go to our website, solidstatecontrolsinc.com, and go to the Contact Us page as well. One last thing before I leave, you will receive a survey after this webinar is complete. We would really appreciate it if you fill out the survey. We're always looking to improve. We're always looking for topics to run our next webinars on. So if you have a specific topic regarding UPSs or batteries, then please get in touch with us through that survey. I read every single one of the surveys and let us know what topics you would like to see in the future. And I would be delighted to make that happen. So we've got no more questions, which is great. So thank you everybody for joining us on Wednesday, the 15th of February. I hope everybody had a good Valentine's Day yesterday. Enjoy the rest of your day. Enjoy the rest of your week. And we will speak to you again in 1 month's time. Look out for the notifications for when the next webinar will be. Take care, and thanks very much.